Hey Aaron, here's exam 3, essay 1. It's really fast. We're going to cover algorithmic cells and then ventricular muscle cells or myocardium. And we're just going to cover their action potentials, then we're going to move on to ECG. So what's happening here, they both have a really low resting membrane potential because in these cells it's called pacemaker potential. So what happens is in algorithmic cells we have an increase from resting, and then once it reaches threshold it has a big action potential, comes down back to resting, and then slowly slopes up back again to the threshold. So what's happening here, this is phase 4, phase 0, and phase 3. So in phase 4, we have these HCN channels, which are called the funny channel, also referred to as IF, the current of the funny channel. What's going to happen here is it's going to allow some sodium in, which is going to increase until it crosses threshold. So these are activated by repolarization. So when this repolarizes down here, it opens these channels and causes it to increase until it crosses threshold. At threshold, calcium L-type channels are going to open, also referred to as current of calcium L. The calcium channels stay longer open than sodium channels do, so we have this wider top or wider action potential than we normally are used to. As we reach 3, we're going to have potassium channels open, or the current of potassium channels, which is going to decrease and repolarize the cell, and this will repeat over and over again. So with muscle and myocardium cells, we're going to have our resting membrane potential, and then this graded potential is actually caused by these autorhythmic cells. The cells are attached to each other, and between the cells they have gap junctions, so the action potential can move from one cell to another. So that's going to cause a graded potential in the cell, which then causes an action potential, the sharp decrease, and then a plateau phase, and then back down to our resting membrane potential, and that repeats. So what's going to happen, we're going to call this phase 4 again, phase 0, phase 1, phase 2, and phase 3. So if you see, this one just doesn't have phase 1 and 2 versus this one, which has all 5 phases. So in phase 4, once again, we have these potassium channels open, which is going to maintain this low resting membrane potential. As it crosses threshold, we're going to have sodium channels open. These sodium channels, voltage-gated sodium channels, will cause the increase really fast. When we reach the top here, what's going to happen is, starting here, we're going to have the opening of what we call the TC channel. As the TC channel opens, there's 2 types, 1 and 2. One is a potassium channel, the other one's a chloride channel. Those both are going to quickly repolarize the cell and then close. Or no, so they're not going to close, sorry. They're going to quickly repolarize the cell. And then when we hit this plateau phase, what's happening is calcium L-type and T-type channels are opening, increasing the positive slowing in, plateauing it. And during this phase, we also get what we call ultra-rapid potassium channels, rapid potassium channels, and slow potassium channels. So incrementally, each one of these is going to open, and eventually it's going to be enough to lower the membrane potential back down to our -90. So those are all the channels involved in each of the different units. And then, of course, in 4 again, we're going to have the potassium channels. So those are kind of how the action potentials work, and how the ion currents move through the cell to create these different action potentials, right? So in the heart, we don't really measure action potentials. Instead, we're going to measure electrical force. So if we have a heart and we put 2 leads, a negative lead and a positive lead, we're going to calculate a change in magnetic field. So it's happening if we had 4 cells right next to each other. If they all outside all starts positive, if all of a sudden one of the cells becomes negative, now there's a differing pole and we're going to get a magnetic field. So as this perpetuates down, the magnetic field will cause a signal. So if the tail is the opposite sign of the vector pointing towards the node, it's going to be a positive, registered as a positive scan versus a negative scan. So that's what we call an ECG or EKG. We're going to start resting at 0. We're going to get a couple of different waves here. Then it's going to repeat. So this is called the P, the Q, the R, the S, and the T waves. So the P wave, what's happening at this time is it's atrial contraction. So the atrium's contracting, and as the atrium contracts here, we're turning these cells negative, and we're moving down, so that creates a vector towards the plus, which is going to cause a positive deviation. Then as we reach the R, the septum in between the two ventricles, there's going to be a starting depolarization here in the middle, but it's mostly going to be pointing up. Well, there's vectors pointing almost everywhere, but the sum vector points towards the negative with a negative node. This causes a negative deviation. So the Q is the intraventricular septum depolarizing. So then, as that signal from our intraventricular septum perpetuates, eventually it's going to reach towards the bottom of the apex. We're going to get all these electrical signals down here causing our R wave. So our R is the depolarization of the ventricles, particularly towards the apex. And then we get this S wave because at the very end, this our lateral superior ventricular wall is going to be the very last one to depolarize. Because of that, we're going to have all these vectors, but the sum vector is more towards the negative than it is the positive, so it causes a slight deviation. So now the whole thing is depolarized, and as it repolarizes, right, we're going to have all these negative cells, and they're slowly going to become positives going upwards. That's going to cause another bump called the T wave. So this is the repolarization of the ventricle. So this is super important because we can use this to detect certain diseases. For example, we're going to talk about NSTEMI. So these are types of heart failure caused by hypoxia. So inside the heart, we have a coronary artery that feeds this lower part, or well, it feeds the whole heart. But down here sometimes, if we have little blood flow or a blood clot or something happening up here, these cells down here in the lower ventricular wall, they're not going to get enough oxygen, and so they don't work as well. And so what happens is some of the endocardium might remain depolarized. So it's going to happen, right? We're going to have some negatives, and they're not going to cause action potentials. They're just going to sit here negative the whole time. And so what happens with our nodes is that's going to cause some changes. So an EKG machine, we'll just draw right here. Our EKG machine, right, is going to sense our P wave, our S wave, our R wave, or Q, R, S, and then our T wave. But the because of our body having muscle contractions and neuron signals, there's lots of electrical signals, it tries to negate any constant signals, right? So because this is a constant signal, right, after a normal beat, if this started to happen, what's going to happen is this is now going to ignore this. So if we made the sum vector it would be a positive deviation. So we're going to go up. Now we just have a new baseline above 0. So now at this new baseline, what's going to happen, we're going to get our P wave just like normal, our Q wave, our R wave, but this time our S wave. What's happening in the S wave, right? End of the S wave, all of these cells are depolarized, which means we have to come back down to 0. And then it's going to go back up and go to the T wave. So sometimes there's an inverted T wave here or whatnot, but the importance to recognize STEMI is that the S wave is lower than the end of the T wave. And this is not good. It's not going to kill you necessarily, but it leads to STEMI. So in STEMI, what's happening in the center, this heart, is in this wall, all of this chunk, they're all negative. What happens is now it's going to send out all these vectors, and the sum vector is going to be pointing towards the negative. So if we start off with our regular wave again, this is going to then cause a negative deviation. So when it measures again, we're going to get our normal waves, right, till we hit R. Then once we come back to S, when all of them are negative again, it's going to be 0. So we have to return to this other 0, right? This is 0. We have to return to 0. And then this S wave, we'll then go to the T wave, which connects back down to our new baseline. So in this one, our S wave is above the end of the T wave. So that distinguishes STEMI. And so when this happens, this eventually can cause, for example, ventricular fibrillation or something else to cause the heart to stop working properly, and can kill the patient if there's no intervention. So yeah, we'll wrap that up. We're going to move on to mechanisms that the heart uses. So we have 2 receptors. We have beta 1 receptors and we have M2 receptors on the heart. This is the parasympathetic, and this is going to be the sympathetic system. This is going to come from the vagus nerve, right? So our beta 1 receptors are going to respond to norepinephrine, and then our M2 receptors are going to respond to acetylcholine. So we're just going to go through a couple of different ways that the heart is regulated using these things. So every time we use beta, remember norepinephrine. Every time we use M2, we're going to talk about acetylcholine. And so I just wanted to then define a couple of terms. Ionotropic refers to contractility. So it's increasing the force in the heart. Lusotropic refers to an increase in speed of relaxation. So a lusotropic effect is saying because this receives the norepinephrine, it's not going to relax as long. And so when we talk about that, it's going to increase or decrease the time of contraction. So then our last term I want to talk about is chronotropic. So chronotropic is heart rate regulation. It's how these two together can increase or decrease heart rate. So let's just start with ionotropic. We have our beta 1 receptor receives norepinephrine. It's going to signal an alpha 1 subunit. This alpha 1 subunit can do a lot of different things, but we'll just start by talking about phosphokinase A. So it's going to activate phosphokinase A, and this is going to activate or phosphorylate 4 different things. So I'll just write P for phosphorylate. So the first thing it's gonna phosphorylate is what's called the DHP channel or L-type calcium channels. When this happens, it's going to increase the probability that it opens. That increased probability is going to lead to more channels open. So there's going to be a calcium influx. When that calcium influx occurs, there's going to be an increase in concentration in intracellular calcium. And this is going to cause what's called a calcium-mediated calcium release. So that means the RYR is going to release calcium into the cytoplasm, which is going to cause a silicon contractile. This is going to increase contractility. If this happens, that means more calcium is being released, which means the heart's going to contract harder, have more force. So next thing, it can phosphorylate. It can phosphorylate the ryanodine channel. And so when this happens, calstabin 2 is going to dissociate. Dissociate. It's going to leave. And when calstabin leaves, what's going to happen is it's going to open our wire channels. When this happens, it's going to increase intracellular calcium, which is going to then also increase contractility. So, two other things that phosphokinase A can phosphorylate. It can phosphorylate what's called phospholambdin, or it can phosphorylate troponin on the I subunit. So when phospholambdin is phosphorylated, it's going to increase the activity of circuit 2 pumps. When circuit 2 pumps are activated, that more increasing, right? We're increasing the activity. When that activity increases, that means there's going to be an increase in calcium inside the sarcoplasmic reticulum. If that's the case, then that means there is a decrease in the duration of contraction. That means calcium's leaving faster, the heart relaxes faster, increase in speed of relax, which means there is a decrease in duration of contraction. So this speed of relaxation, this is lusitropic. Versus contractility, these two here, these ionotropic. So, same thing with, one thing I forgot. If there's more calcium inside the smooth ER, or the sarcoplasmic reticulum, sometimes it can cause RYR channels to open, and I'll follow that pathway. So when it phosphorylates tropomyosin in the I subunit, this causes an increase in release from the C subunit. So calcium is released. If calcium is released from the troponin, that's going to be taken up by the circuit pump. This is going to increase the speed of relaxation. So speed of relaxation is faster. This is a lusitropic effect again, which this causes a decrease in duration. And then we talked about this a little earlier, but the last thing this alpha subunit can do is it can interact with the calcium L-type channel directly. This is going to increase the probability it opens. This is going to increase a calcium influx. If the calcium comes in, it's going to increase intracellular calcium, which is going to cause a calcium-mediated calcium release, which is then going to increase contractility. So I hope all that makes sense, but basically, when this beta subunit is activated by norepinephrine. All of these things are happening simultaneously to increase contractility and decrease the relaxation time needed. So these lusotropic and isotropic effects happen, which enable the heart to beat faster. So now, with chronotropic actions, we're going to talk about positive with beta 1, and then we'll talk about M2. So what happens is when beta 1 receives norepinephrine, something else that happens is it activates adenylyl cyclase. When adenylyl cyclase is active, it increases the amount of CAMP that's in a cell. Increased amounts of CAMP can also activate the funny channel. So that's going to increase the IF, or we could say the HCM channels. They're working more, which means, or they're more open, so that means more sodium is going to come in. This is going to increase the steepness of depolarization, which is going to increase heart rate. So if we come up here a little ways, right here, we're increasing this step right here. So it's going to be steeper, causing more action potentials, meaning more contractions, meaning more heart rate. So CAMP can also do something else. It can increase the amount of calcium in the cell. It can open some calcium or some ion channels and release calcium into the cell. So this can do two things for us. First, when calcium comes in the cell, it's going to increase ICA. This is going to lower the threshold. You can kind of group those into one step, and then this is going to cause an increase in heart rate. The other thing it can do is it can increase intracellular calcium, which once again is going to increase the steepness of that line, which is going to increase the heart rate. Okay, so then with M2 receptors, we have 3 paths. It's going to activate either the alpha subunit, or it's going to activate the beta gamma heterodimer. So beta gamma heterodimer is going to activate what's called the Gerk cell, G-activated potassium channel. This is going to decrease the pacemaker potential. And a decrease in the pacemaker potential is going to decrease the heart rate. It's going to lower the potential. So the other two things it can do, these are the same. It's going to lower CAMP. So it lowers CAMP. What's going to happen is this is going to decrease IF. It's going to decrease the funny channel. What happens there, if it decreases that activity, it's going to flatten the slope of that line, which causes a decrease in heart rate. So over here, another effect that CAMP has is it decreases the calcium flow. Less calcium means that threshold increases, or that threshold is farther away. This distance is going to get farther away from our pacemaker potential. This also causes a decrease in the heart rate. So these are kind of all the mechanisms you're going to use in the heart. So real fast, I just want to draw a muscle cell. So those are all, these things up here, they're going to happen on pacemaker cells, and then I'm going to show how this affects a muscle cell and how calcium plays a role in muscle contractions. So like always, we got our sarcoplasmic reticulum here, but this time there's no joint activity between DHP or calcium L type what happens is when we reach membrane potential, L-type opens, has calcium come in. This calcium activates the ryanodine channel, and calcium comes out. Calcium comes out of the sarcoplasmic reticulum and causes the actin and myosin to contract. Now, to mediate this, when the muscle cell no longer wants to contract, we have the circa pump, which is going to be use ATP and pump calcium back into the cell. But this extracellular calcium that came from the extracellular space, we need another channel. So this is going to be a calcium sodium channel. A pump, sorry, this is a secondary active pump. Doesn't use ATP, but for every 3 sodiums, it's going to pump out 1 calcium. That's going to regulate the levels of the sodium. And then as always, we have our sodium potassium pump. Sodium potassium pump here using ATP to regulate the amount of sodium in the cell. So that's going to roll calcium in the cell, and the mechanisms in the cytosol to return the calcium to the sarcoplasmic reticulum and extracellular fluids. So finally, the last thing we're going to do is what is called the cardiac cycle. So I'm hoping to be able to get this all on the screen at once, but basically this is the cycle of pressure, blood volume, and stuff happening throughout the heart. So we're mostly going to focus on the left ventricle, because that's where most of this is measured, and this is how blood gets to the body. So on this side, we're going to put pressure. We're going to draw a couple things. First thing that I want to draw is the atrium. Wait. Oops. Sorry, that was wrong. It's going to come down. Increase in pressure. And then it's going to start filling up. And then decrease. Until we hit another bump. Okay. So what's happening, if this is the atrium, on this we have a couple of valves. We have our bicuspid. We also have our semilunar valve, or aortic semilunar valve. So here's the aorta, and here's the bicuspid valve that leads to the atrium. So the bicuspid valve is open. Blood flows into the ventricle. It does most of it passively, but right at the end, we have atrial systole. It's going to pump, increase in pressure, pump in that blood into the ventricle. So the ventricle here is going to fall right behind, have less pressure than this aorta until it finishes pumping. It's going to spike up and come back down, and then follow the atrium here again. So what's happening here is this is the start of systole. Oh, spelled that wrong. So when the ventricle is contracting. So here's where we see our first heart zone, right here. You notice that the pressure of the ventricle is greater than that of the atrium. When the pressure is greater than that, it pushes blood back, closes this bicuspid valve, and we get sound 1. It's the bicuspid valve closing, also referred to as lub. So then if we go up here, we draw the aortic pressure. The aortic pressure is going to be it's going to be a lot higher than the ventricle until it pumps up. Then the ventricle is going to increase here. Okay, so here's the aorta. So what's happening here is having a decrease in pressure because it hasn't received blood in a while. The ventricle contracts, opens the semilunar valve, blood flows into the aorta until it reaches resistance. So once the ventricle has finished its contraction, it's no longer pushing blood. The pressure takes a few seconds, then it returns. And that return, if we draw the aorta right here, right, we have our semilunar valve. It's open, right, blood flows. And then once the, whoops, that's the wrong way. The semilunar valve opens this way. Then once the blood reaches its maximum, it takes a few seconds, well, not a few seconds, a few milliseconds, and then it turns around and comes against these flaps, closes the semilunar valve, and then a bunch of pressure builds up as it hits the end of the aorta. This is called the dicrotic notch. It's a sign of the end of systole and the beginning of diastole. And then this cycle continues. So what's happening here is with the closing of the semilunar valve, we get sound 2. Semilunar valve closes. So this is referred to as dub. So we get lub, we get dub. So sometimes if we hear a shushing sound or something, if it's closest to lub, that means there's a problem with the bicuspid valve. However, if it's closest to dub, that means there's a problem with dub. These could be tubes that are too small, or maybe the bicuspid or semilunar valve are really constricted, or there's a pinch somewhere in the aorta which could cause this shushing sound, which would be a third sound. So now we're going to compare this pressure to volume. So this is how much blood is in the ventricle one time, and we're mostly just going to look at the ventricle. So getting an increase in volume, and then the aorta contracts, then we get a flat spot for a few seconds, then a huge decrease, then we increase gradually, and we repeat. So what's happening here, this will be a longer. So what's happening here is we have two flat spots. Both are equally important. So if we look kind of up at this graph above, this peak aligns with the atrium's contraction, increases in the volume. It then sits for a second, and as it sits, it's building up this pressure here until it's above the aorta. So it has the same volume. This is called isometric or isovolumic contraction. Then as the blood flows out of the ventricle as it contracts, it reaches a new point. And this is about roughly after contraction is complete, right about here, right? The bicuspid valve is going to open again. It's going to start increasing, but in between the bicuspid valve opening and the semilunar valve closing, we have this short area. This is called the isovolumetric. And that's contraction, so this is relaxation. I think it's metric. And then this cycle repeats. So if we compare this to an EKG, what's going to be happening is here we're going to get our P wave. Then we're going to have our S, or our Q, our R here as it spikes. We're gonna down to our Q, and then over we'll get our T wave. So this all happens during our systole period. We'll get our T wave, then it restarts. As this fills up and this spikes in, we're gonna get our P wave, then our Q wave, then our R wave, then our S wave, and our T wave finally. So this shows all the opening and closings of valves, right? Closing a bicuspid, opening a bicuspid. Opening of semilunar, closing of semilunar, shows our pressure changes, our blood volumes at various stages, and this will be the whole cardiac cycle. So this repeats over and over again in your heart. The difference between our max and our min is how much blood we're pumping, but I think we'll save that for another video. Thanks, Aaron, for watching.